Hello student, today we are going to see successive differentiation. In previous lecture we have seen one theorem on differentiation. So in this lecture we will see successive differentiation. What do you mean by successive differentiation? If you differentiate one function again and again, then that function, say that successive differentiation function. Okay, so we will see the simple form of the successive differentiation. Let f of x equal to y be any function, then y1 equal to f dash of x is called as a first order derivative. It is called as a first order derivative. Y1 means this represent as a differentiation with respect to x. Then it can be written as y1 equal to f dash of x, or it is written as dy by dx. This is also called as dy by dx, or it is also called as f dash of x, or this can be written as y1 equal to f dash of x. So this is the first order derivative of the function f of x. Now what is the second order derivative? If you differentiate this function with respect to x, so again differentiate this function with respect to x, then we get d2y by dx square. This can be written as y2 equal to f double dash of x, differentiating with respect to x to f dash of x. Okay, so this is called as a second order derivative. Similarly, if you differentiate this function third time, if you differentiate this function again, then this can be written as we get d cube y by dx cube, and it is written as y3 equal to f triple dash of x. So this is the third order derivative of the function y f of x. Okay, so this is the first order, second order, third order derivative. So in this way we can find out the fourth order, fifth order, sixth order, and so on. So generally the derivative in successive manner are denoted by y1, y2, y3, and so on yn, where yn is called as the nth order derivative. So in this way we can calculate the first order derivative, second order derivative, third order derivative. First order derivative means first derivative of the given function, differentiation with respect to x. Second order derivative means differentiate two times to the given function. Third order derivative means differentiate three times to the given function. So this is the simple uh, definition of the successive differentiation. So we will see one theorem on this successive differentiation, that is a Leibniz rule. That is a Leibniz rule. What is the statement of the Leibniz rule? Let u and v be the two derivable function of x having nth order derivative in interval ab. We can take interval ab, you can take any other interval. Then the product uv also have the nth order derivative in interval ab. Okay, so the nth order derivative of the function u and v, because u and v are the two variable, then the derivative of the two variable is u v n, this represent as a nth derivative, equal to u n into v, derivative of first function, nth derivative of first function into second function, plus nc1 means u n minus 1 derivative of n minus 1 v1 derivative, then plus nc2 u n minus 2 v2, plus and so on, last term is u vn. So this is called as the nth derivative of the variable uv. Okay, so this is the nth derivative formula of the Leibniz rule. Now we will see the we have already discussed this part in previous lecture of a differentiation. So already we have seen f of x plus minus g of x bracket derivative, that is it is called as the f dash of x plus minus g dash of x. We have already seen in previous lecture. This is also we have seen in previous lecture third property, that is a multiplication property, f of x into g of x bracket derivative equal to f dash of x plus into g of x plus f of x into g dash of x. Okay. Also we have seen this property k into f of x bracket derivative equal to k f of x, where k is a constant. Also we have seen this term, that is division derivative, f of x divided by g of x bracket derivative equal to, this can be written as g of x into f of x minus f of x into g dash of x divided by g of x bracket square for all x belong to AB. So this is already we have seen in previous lecture. Now we will see the complete proof of the Leibniz rule. We have already seen the statement of the Leibniz rule. So again we will see the statement of the Leibniz rule. So what is the statement? Let u and v be the two variables of the function x having nth order derivative in interval AB. So here we have taken interval AB. Then the product of uv also have the nth order derivative in interval AB, and that product is given as equation number 1, and that is equation number 1 is uvn equal to un nth derivative into second term plus nc1 unc1 v1 plus nc2 un minus 2 v2 plus and so on u vn. So equation number 1. So this is the Leibniz rule of the, that means we can say the nth product of two variable, and that is given as equation number 1. Okay, now we will see the proof of this Leibniz rule. Okay, so before going to start proof of this theorem, we will solve this problem, we will solve this theorem by using mathematical induction method for n equal to 1. Okay, so we show this method of a mathematical induction for n equal to 1. Generally we will see for n equal to 1. Okay, so using equation number 1 for n equal to 1. Okay, so put n equal to 1 in equation number 1, you will get uv1 equal to dd of dx uv. What is the meaning of this? First derivative of this term. So one means differentiation with respect to x. Okay, so by using product rule, our general product rule, second function into derivative of first function plus first function into derivative of second function. Okay, so du by dx, it is denoted as a u1. Okay, this is the notation, this is the notation of the du by dx, this is the notation u1 means du by dx, and this v term is as it is, plus u term as it is, dv by dx means differentiation with respect to x, and it is denoted as a v1. So this is the notation of this term v1. Okay, so in this way we can write the first order derivative of the term uv1 equal to u1 into v plus uv1, means derivative of first function into second function plus second function first function into derivative of second function. Thus we can say that this result is true for n equal to 1. Okay, now we will prove this theorem for n equal to k. So now suppose that this result or this theorem is true for n equal to k. Now for put n equal to k in equation number 1, we get that is product of uv k derivative, this can be written as ukv plus kc1 uk minus 1 v1 plus kc2 uk minus 2 v2 plus and so on u into vk. Simply you have to put n equal to k in this equation number 1. Okay, now we will differentiate this equation with respect to x. Now differentiate with respect to x, so this can be written as uv in k uv here here is a mistake, so u k plus 1, so here is k plus 1, k plus 1. Okay, so equal to u k plus 1 means derivative of first function into second function u k plus 1 v into plus first function into derivative of second function, that is uk into v1. Okay, this term is complete. Now second term, kc1 as it is, kc1 as it is. Now we will apply product rule for this term. Okay, okay, so what is the product rule for this? uk derivative of first function, that is into second derivative of first function into second function, uk v1 plus uk minus 1 v2. Okay, derivative of first function, that is into second function plus first function into derivative of second function. In this way we can write. Okay, so here uk minus 2, so here k minus 2. Okay, k minus 2. So plus third term plus kc2. So again we will use here product rule, kc2. Again we will use here product rule, that is uk minus 1 v2 derivative of first function into second function plus second function derivative of second first function. Okay, so in this way we can write this term. So plus and so on. Last term is u1 vk plus uk plus 1. So in this way we can write the term. Okay, so what is next step? We will take uk v1 uk minus 1 v1 common term from this term. So left hand side uv into uvk plus 1 means k plus 1 derivative equal to. Okay, so from this term uk plus 1 v as it is. So here plus, there is a print mistake, so here may plus. Okay, then what is next term? Now we will take uk v1 is common term from this term. Okay, so what is remaining here? Here 1 plus kc1. If you multiply this term, so you will get kc1 uk v1. So uk v1 take common. So what is the remaining term? In bracket 1 plus kc1. So plus term as it is, this plus term. Now take common uk minus 1 v2, uk minus 1 v2 from this and from this. So what is the remaining? If you multiply kc1, so you will get kc1 plus, and this term is kc2. So you can take common uk minus 1 v2 from this and from this. So in bracket term is kc1 plus kc2 into v2 plus and so on, and last term will be uk plus 1. So in this way we can write down we can take the derivative of the term uk. So we know that we will find the term, that is 1 plus kc1 and kc1 plus kc2. We know that the result kcr plus kcr plus 1, which is written as k plus 1cr plus 1. So for r equal to 0, 1, 2, 3, we can find out kc0 plus kc2, which implies 1 plus kc1. So which is implies 1 plus kc1 equal to k plus 1c3, k plus 1c1. Okay, so which implies now kc1 plus kc2, so which implies k plus c1. So we will put all these values in this equation. So we will get uv k plus 1 derivative equal to u. This term is k plus 1 into v as it is. So here is plus term. So this is plus term. So plus k plus 1 c1 uk, k plus 1 c1. Where is this term? K plus c1 into this is a multiplication bracket term uk v1 plus k, so here bracket k plus 1 c2 uk minus 1 v2 plus and so on u v k plus 1. Okay, so now what is next? So u left hand side as it is, uk plus 1 into v plus k plus 1 c1, k plus 1, so this is a bracket k plus 1 c1 uk plus 1 plus minus 1 v1, then plus k, so plus k 1 c1, so here is a bracket here is bracket v2, and last term is u k plus 1 as it is. So this is the this term is true for k plus 1 term. Okay. Now, if it is a true for n equal to k, then the above result is true for n equal to 1. So thus the result is true for all the values of n, and hence we have uv nth derivative equal to unv plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus and so on u into v1. So this is the complete proof of the Leibniz rule. Okay, so this is the complete proof of the Leibniz rule. Now we will solve the next problem by using Leibniz rule. Okay, so what is the problem? So we have given if y equal to e to the power sine inverse x, then prove that 1 minus x square into yn plus 2 minus 2n plus 1 x yn plus 1 minus n square plus a square into yn equal to 0. We have to prove this result. Okay. So what is given that? So we have given y equal to e to the power a sine inverse x. Okay. Now differentiate with respect to x. So take the first order derivative. So dy by dx, this can be written as y1. So dy by dx means, so dy by dx can be written as y1 equal to, so what is the e to the power x means e to the power a sine inverse x as it is into derivative of this term, that is a into sine inverse x. We know that the a into sine inverse x is, a is constant, so a upon a under root 1 minus x square, that is the derivative of the sine inverse x. Now multiplying on both sides under root 1 minus x square, or we can multiply this term to this term. So under root 1 minus x square into y1 equal to a e to the power a sine inverse x as it is, right hand side. So again differentiating on both sides with respect to x. So we get derivative first function into derivative of second function plus second function into derivative of first function. Derivative of root x is under root 1 upon under root 2 root x. So this can be written as 1 upon 2 under root 1 minus x square into derivative of x square means minus twice x. So we can write left hand side in this way, totally in this way, equal to right hand side a is a constant, derivative of e to the power a sin inverse x means e to the power a sin inverse x into derivative of this term, that is a upon under root 1 minus x square. So again multiply under root 1 minus x square on both sides. So we get under root 1 minus x square y2 minus, so this minus so this 2 and this 2 get cancelled. So what is remaining is x y1, and under root 1 minus x square will get cancelled. What is remaining is x y1. A square y, a square y means we know that y is e to the power, we have given e to the power a sin inverse x. So instead of e to the power a sin inverse x, we can put y from equation number 1. Okay. So what is next step now? So 1 minus x square y2 as it is minus x y1 as it is a square y. So if you transfer this term to left hand side, we get, so we can write y2 1 minus x square, okay, minus y1 x1 minus a square y equal to 0. Okay. So we know that y is, we have given y is e to the power a sin inverse x. Okay. So this is the nth derivative. Okay. Now taking the nth order derivative and applying the Leibniz theorem. Okay. So take the nth derivative of this term. Okay. So this is the first order derivative, and if you apply the Leibniz rule for this equation, we get y2 1 minus x square bracket n minus y1 x bracket n minus a square yn equal to 0. N means nth derivative of this bracket. Okay. So apply the nth order derivative, or we can say that Leibniz rule. So we can write this step as y n plus 2 1 minus x square derivative of first function into second function plus yn plus 1 second function into derivative of first function. Okay, so yn plus 1 minus twice x plus n into n minus 1 upon 2 factorial yn minus 2. So third term is minus yn plus 1 x plus n yn 1, and last term is minus a square yn equal to 0. So in this way we can apply the Leibniz rule to this term. Okay. Now what is next step? Now take yn plus 2 as it is, term 1 minus x square yn plus 2 term as it is. Now here we will take n yn plus 1 and x common term from this term and this term. So what is the in bracket? So here is 2n and here is plus 1. So minus x yn plus 1 take common term. So in bracket is 2n plus 1 minus. So minus n minus 1. Okay. So these 2 and these 2 get cancelled. Okay. So n minus 1 plus. Okay. So what is here? Plus n a square plus n a square. So we can take here y1, yn, and yn is a common term. So what is in bracket? So this is n minus 1. So plus, so this is plus term minus plus n plus a square yn equal to 0. So take the yn from this term common. Okay. What is next step? So first step is 1 minus x square yn plus 2 as it is. Then second term 2n plus 1 x yn plus 1 term as it is. So multiply this term to this bracket, that is n into n square minus n plus a square yn term as it is. So what is next step? So this term is as it is, 1 minus x square into y n plus 2. Then what is next step? 2n plus 1. So this term again as it is. Now so this n and this plus n get cancelled. So n square plus a square into yn equal to 0. So this is the nth order derivative of the given function y equal to e to the power a sin inverse x. Okay. So this is the complete proof of the given term.